Good afternoon. Most of us are familiar with wearable tech like the Apple Watch, but these devices won't become massively adopted until they're made stretchable. If the promise of continuous health monitoring is going to be true, these devices have to integrate with us in a seamless way, much like comfortable clothes or even like a tattoo. This is important for massive adoption of these devices, but also for specific application cases, such as the health monitoring of a newborn baby who needs to be very comfortable. Unfortunately, electronics today are mostly rigid. They're a stack of ceramics, metals, semiconductors, plastics that don't take too much deformation before they break. One way to get to stretchable electronics is to replace some of those materials by nanomaterials. Take, for example, a nanowire, which is a tiny strand of metal, 1,000 times thinner than a human hair. You can make a network out of these, and this network can replace a solid film of metal. That's because the network still conducts electricity, but it can accommodate much more deformation. But of course, we don't know what is the upper limit of that deformation because we don't know the properties of each individual nanowire. We would want to stretch these wires and figure out how much force and how much deformation does it take for them to break. And we want to do this for many of them because remember, we're using millions of them in these devices. This is challenging, but we've solved this challenge in my lab by patterning a bunch of these nanowires in an aligned way on top of a rubbery polymer. We stretch this rubbery polymer while looking at this process in the microscope. In that way, we can track all these nanowires up until they fail, and we can capture data for a bunch of them and the statistics of their failure. We've had to develop statistical theories to deal and interpret this data, and we've had hundreds of data points, which constitute a statistically significant data set. Furthermore, we're doing this with other nanomaterials, such as graphene, which you see on the last slide, which is a 1-atom thick nanomaterial, also a potential candidate for stretchable electronics. We hope this information will be useful for engineers in the future to design reliable, truly stretchable electronics that are adopted massively by all of us. Thank you.